from 3, 2, 1, then we're good. Okay. So anyway, you know, whether you did this cultural Thanksgiving thing or not, I think it's good to just take time to be grateful and thankful, and just think of the things that you are grateful for. I don't know. I'm thankful for you, my students, for giving me the job that I love. I love teaching, and I love having you guys as students. I love I don't know, being in this class, and so I'm thankful for you guys. There's lots of things to be thankful for, and that, you know, today's not about that, but I do encourage you guys to just spend some time, and if you are going home to be with your family, you can say your professor suggested that as a family you go around and you share some things that you're thankful for. If you don't do that already, maybe that's something you guys already do as a family, but I think it's good. I think gratitude is like an opposite feeling of envy and anger and jealousy. So it's hard to be envious when your heart is full of gratitude. So anyway, we'll talk Monte Carlo methods now. So, okay. Anyway, happy Thanksgiving, everybody, and enjoy your time off. And yeah. Okay. So let's talk. So on Monday we covered. So we're kind of in this section for multivariate Markov chain methods, okay? And in all of these things, right? So with Monte Carlo methods, the goal is to estimate some function so just going back to the big picture, right? Just so we don't lose sight. Monte Carlo methods, we want to estimate function values you know, via random sampling. So we might want to get, you know, what is the expected value of h of x? And this is the integral of h of x times f of x dx, right? Where x is defined by the PDF f of x, right? Okay, so anyway, and but this time x could be multivariate, right? So x, and the way we do this, so the Monte Carlo method is sample like 1,000,000 values of x, right? And then calculate, calculate h of x for each value, and then what do? Take the mean. All right, so this part's easy. Calculating h of x and taking the mean, that's easy. This part, it's usually, this is where we spend a lot of time here. Okay, we said, all right, we had the kind of the independent methods, the rejection sampling, the inverse CDF, and then we said sometimes those don't work out well, so let's do the Metropolis algorithm, okay? And so we spent a lot of time just talking about how can we get like 1,000,000 values of x from some PDF, okay? And now we're doing the exact same thing, it's just multivariate, okay? Same idea. We still want to get this estimate. We still want 1,000,000 values drawn from this PDF. we still just calculate the function. We would still just do the mean. Okay, to do all of this, now we have a multivariate thing. And on Monday I said the Metropolis algorithm works fine, but sometimes you're rejecting a lot of things. Okay, so multivariate Metropolis will work, but can be inefficient. All right, so in high dimensions, proposed values may not be frequently accepted. Or maybe I should say frequently used. Slash accepted. Okay. So you've got some kind of proposal thing. And so what we have is we've got the Gibbs Sampler. Okay, so the Gibbs Sampler is another Markov chain Monte Carlo method. So our MCMC. It's another MCMC method that is used to generate a sample of X, I should say of a multivariate X. Okay? So, same idea. We just want like 1,000,000 values of X from something, and we want like a multivariate thing. All right. So the way we do this is we break our multivariate function into a bunch of individual conditional distributions, right? So your PDF, the target distribution, is a multivariate, we might call this a multivariate joint distribution. Okay, and this multivariate distribution could be difficult to sample from directly. And it could also be inefficient to sample from, via Metropolis. And so what we'll do, our solution is the Gibbs Sampler. And what this will do is we break down the joint distribution into several univariate conditional distributions. Okay, so we break them down into several univariate conditional distributions, And these univariate distributions should be are easy/easier to sample from. Okay. So let's say we're going to do the multivariate normal PDF. So let's say our target multivariate normal distribution. And again, we're going to pretend it's difficult to get sample from this directly. Okay, and so you've got here. You have a two-dimensional multivariate normal, and we'll say you've got mean vector mu and variance covariance matrix sigma, and your contour map will look like this, right? Okay, so this is your multivariate normal. This is kind of your contour of the densities of the density, right? Like if I had graphed this, it would look like I don't know how to draw this thing, right? So on the I got this hill-looking thing. Does that? I don't know if this looks anything three-dimensional. Okay, but anyway, all right. So anyway, you got this smooth-looking hill, supposed to be, all right, and we want to draw samples from this. Okay, so the idea here is that we are going to almost like slice the distribution. Okay, and so here we've got x1 and we've got x2. This is our joint density. This is the contours of the, I should call this our joint density of x1 and x2. All right. And what we'll do is we're going to just break down. So we have our vector x being x1 and x2, which comes from this two-dimensional normal, and we're going to kind of break it down into x1 comes from a normal distribution that something given that x2 is fixed at some x2 value. x2, I'm going to just write at time t, right? So that we condition x1 is conditioned on x2 being equal to our current value of x2. And then once we get that, we condition it on x1 being conditioned, right? So then we we draw x2 from a distribution where we've conditioned x1 on a value. Okay, and so what this looks like is, maybe we start off with x2 fixed right here. So this will be our kind of our starting x2. Okay, and so here I'm just gonna take a slice, right? And so you can imagine here I'm slicing the plane right here, okay? And it slices back over here, and when it encounters the hill, so just imagine this slice going through the hill here, okay? If we are able to kind of just look at the thing, there is like it's just a univariate normal. So it's I guess I don't know how to draw this. Okay, if I slice this out, it's just going to look like this, right? It's just some normal distribution here. Okay, so this is kind of probably our peak value here, and we just have this this normal distribution centered kind of at the peak there, and we draw a random value from this normal distribution. Okay, and so maybe by random chance we end up right here. Okay, so this is our random x1 value. Okay, so maybe we end up right here. Okay, and so once we do that, we then draw a slice right there. Okay, and so this would be, I don't know, kind of like right here, and so now you've got this picture is getting too crazy. I wish I had like a three-dimensional model. Okay, so we draw a slice here. We've got a normal distribution here. We draw a random value from this univariate normal. Okay, once we have a new value, we draw a slice in the opposite direction. Okay, for the x2, and we have another univariate normal. Okay, so now we've got a univariate normal that looks like this. Okay, at this location, and we might draw a value here. Okay, and or you just by random chance you end up somewhere else. Okay, and so every time you draw, you just slice and update accordingly. Okay, so so this is what it kind of looks like. Is what we have to do is we have to just kind of condition. So the Gibbs sampler requires us to figure out the conditional distribution when you hold the other value constant. And that might be the hard part, okay? Or it is the hard part. When we hold the other values constant, okay? There's something that is reminiscent of coordinate descent for optimization. I don't know if you guys remember that. It's reminiscent of coordinate descent, but in coordinate descent, you just picked the one value that maximized the resulting kind of conditional function, right? So you set everything, you set the other variable equal to a constant, and then you found the value that maximized it. Here, you're setting the other value to a constant, but then you're getting a new PDF, okay? And then you randomly sample a value from the PDF, from that resulting univariate PDF. Okay, so let's see. So let me kind of just show what this might look like, okay? So if we say our vector x comes from the bivariate normal, and just to keep it simple, we'll say mu is equal to the vector 0, 0, and sigma will be, we'll have this, okay? So we'll throw rho in there, and then so our PDF, I'm not able to slide this up, okay. So our PDF looks like this. Is the determinant of 2 pi sigma to the negative 1/2 exp of minus 1/2 x minus mu transpose sigma inverse x minus mu. Okay, and then and so this becomes, if we apply this, we have 1 over root 2 pi, I'm sorry, 1 over 2 pi square root of 1 minus rho squared exp of minus 1/2, and then we've got basically the vector x1, x2, and 1 over 1 minus rho squared times the matrix 1 negative rho 1, and the vector x1, x2. Which we have this, and this is equal to 1 over 2 pi root 1 minus rho squared, and e to the, and if you do all of this math, we get negative x1 squared minus 2 rho x1 x2 plus x2 squared over 2 times 1 minus rho squared. Okay, this is a lot messier than what we might have, okay? All right, and then what we want is to do Gibbs sampling. Okay, like we start at location, let's say x1 at time t and x2 at time t. Okay, so we'll start at this location, and what we do is we sample the next x1 value, from a univariate distribution, where x2 is held constant at our current value. Okay, so what that means is that x1 at time t plus 1 is going to be drawn from a PDF for x1, where we set x2 equal to our current x2 value. Okay, and then once we have x1, the new x1 value, once we have the new x1 value, okay, we sample the next x2 value from a univariate distribution, where x1 is held constant at the value of x1 that we just drew. That we just selected, which is x1 at time t plus 1. Okay? And that will get, so we get x2 at time t plus 1 coming from some PDF of x2 where x1 is equal to x1 at time t plus 1. Okay? And so now, now we have our new location, x1 at time t plus 1 and x2 at time t plus 1. Okay? And then we'll use that for the next iteration and then repeat the process. Okay? So you have this current location, you hold one of the things constant, x2 constant, and you select an x1. And then based on that x1 that you just drew, you select a new x2, okay? And that will give you a new location for x1 and x2, and then you repeat the process, okay? And if it's multidimensional, I don't know what's going on there. If it's more than 2 dimensions, you just do the same thing, okay? Maybe you have 3 dimensions or 4 dimensions, okay? So you set the other, like if you got 4 variables, you set the other 3 constant, and you select x1, okay? And then, and that gives you a new x1, and you plug that one in, and then you're going to select then x2, so you got the newest version of x1, you're still using the old versions of 3 and 4, x3 and 4, and then you select a new x2. And now you have x1 and x2 that are new. You're going to get x3, you hold x4 to the old value, and you use that, and then eventually you update all 4 values, and you have a new coordinate in 4 dimensions. All right, is that okay? Just kind of conceptually? All right, so mathematically, we just have to say, like, all right, well, what does this look like if we do this, right? All right, so the math. The math to find what, let's find the math of probability of x1 where we hold x2 equal to, some value of x2. Okay, so this is going to be equal to the joint distribution of x1 and x2 divided by x2, right? We hold x2 equal to something. And basically, the probability of x2 is going to be equal to the probability of x1 and x2, where you integrate out, you look at all possible values of x1. Okay? And this thing becomes a constant when x2 is set equal to, a constant value. Okay, so when x2 is held constant, the probability of a constant just becomes a constant. So, we can simplify our work a little bit by saying the conditional distribution of x1 given x2 is going to be is proportional just to the joint distribution. Okay, so from earlier, we have this part is equal to 1 over 2 pi times the square root of 1 minus rho squared, okay? And this is a constant. And then I've got exp of negative x1 squared minus 2 rho x1, x2 plus x2 squared. This negative applies to the entire fraction, I should say. Over 2 times 1 minus rho squared. Okay, and so if I just ignore this constant and I split this apart, I'm going to split this fraction into two parts. Okay, I got negative x1 squared minus 2 rho x1 x2 over 2 times 1 minus rho squared times exp of negative x2 squared over 2 times 1 minus rho squared. Okay, so this part is a constant when x2 is held constant. Okay, so that simplifies to just this part, and so here I've got so if I'm just looking at this, I've got exp of, I'm going to split this up into x1 squared minus 2 rho x1 x2, and then I'm going to just do some, I'm going to add rho 2 x2 squared minus rho 2 x2 squared, okay? This is, I'm just trying to complete the square here. Okay, so I can, over here I have x1 minus rho x2 quantity squared over 2 times 1 minus rho squared, okay? So that takes care of this part up here, okay? So this is completing the square, and then I'm going to have multiplied by basically a negative rho 2 x2 squared over 2 times 1 minus rho squared, right? And this part, this is just a constant when x2 is held constant. Okay, so we get exp of negative x1 minus rho x2 squared over 2 times 1 minus rho squared. Yeah. Is this okay? All right. And if we think of, so this is, so we know that rho x1 given x2 is proportional to this, and if we say recall, the function, the PDF recall, I'll say the normal PDF function. Okay, and the normal PDF is 1 over root 2 pi sigma squared exp of negative x minus mu squared over 2 sigma squared. Okay, so that's the normal PDF. Okay, so can we get this? Right, so this is a normal distribution with mean mu and variance sigma squared. Can we get this to be, can we pick parameters for mu and sigma squared so that these are the same. So can we pick parameter values of mu and sigma squared to get the normal PDF to be this, okay? So can we go from here up to here? I should draw it that way. All right, so what would we pick for our mu? Okay, so we'll let, if we let mu equal to rho x2, then we're in good shape, okay? And we'll let sigma squared equal to 1 minus rho squared. Yeah. Okay, so if I let sigma squared equal to 1 minus rho squared, then it'll look just like this, right? Because we know it's proportional to this. We like ignored a bunch of terms. So if we do that, then we're good. Is that okay? Do you guys see that? So if we say let mu equal to rho x2, and we let sigma squared equal to 1 minus rho squared, then what we derived is in the form of a normal PDF. Okay. All right, and so we have the PDF of x1 given x2 is going to be equal to a normal distribution where mu is set equal to rho x2 and sigma squared is equal to 1 minus rho squared. All right, and then by symmetry, we'll have rho x2 given x1 be a normal where mu is equal to rho x1 and sigma squared is equal to 1 minus rho squared. Okay. Okay, so the Gibbs sampler for a I should say bivariate normal distribution with, I should say, target distribution n2 being mu equal to this and 1 rho 1. Okay, so we'll let x at time t be the values x1 at time t and x2 at time t, and then we'll generate the next x, which will be x at time t plus 1, in 2 simple steps. Okay. First, we get the next value of x1 given x2 is equal to our current value of x2, and this will be normal. We set rho, the mean equal to rho x2 at our current location, and sigma squared is equal to that, and then we get our next value of x2 given that x1 is the value that we just drew. This can come from normal distribution where mu is set to rho x1 from the one that we just drew, and sigma squared is 1 minus rho squared. Is that okay? All right, and then so this is your homework, but kind of just want to demo it. But it's really easy, right? Like, I mean, you just code it up. So, you know, we can just say, okay, I don't know, geez, what's going on? Our studio is frozen. Let's try this again. Okay, so let's let rho equal to, I don't know, 0.9, okay? And so we'll do like to generate, we'll call one function generate x1, and this will be a function where we give it our current x2 value, and I guess our row, all right? And then all this is going to be is just return our norm of, what do we use? Mu, mean is equal to row times x2 current, right? So we say row times current x2, and the standard deviation is equal to the square root of 1 minus rho squared. So that's how we generate x1. Is that okay for the function to generate x1? And then to generate x2, this is going to be based on our current x1. And I mean, it's symmetric, so it's silly to, because generating x1 and x2 is like the same thing, it's silly to write like two separate functions. But just for illustration, I'm doing this, okay? But in our case, they're symmetric, so like it's silly to write the two separate things. But I'm just kind of illustrating what we do, okay? And then so we'll just say, all right, so I need a place to kind of store this. All right, so we'll just make a matrix of NA values, and we're going to say how many number of rows will be, I don't know, let's do 100, and number of columns will be 2. Okay, and then we'll let our first row be, I don't know, 3, 4. Okay, so if I just do, so this is what we have. Okay, and then we're going to just do a, for I in 2 through 100, what do we want? Okay, so we'll say current x1 will be x at row I minus 1, comma 1. Is that okay? So I'm just saying, because we're going to start at row 2, and we're going to go to the previous row, first column, that's going to be our current x1. Okay, and then okay, and then we'll call this x2 next is going to be generate x2 based on current x1 and our row value. Okay, and then x, oh, I'm sorry, I have this written backwards. So we're doing x2, x1 next. Okay, and then x2 next is going to be generate x1 using our latest value, which is x1 next, and row. and then we're going to say x in row I is going to be our new values that we just drew. All right. Does that make sense? This makes sense to me, but I want to make sure the code makes sense.
I know it's the same function, but x2 next, you should just call gen x2, right?
Oh, yes, yes. You're absolutely right. Yeah. So we generate x1 based on our current value, okay, and that gives us x1 next. And then, and this is the important distinction, is that we take the value that we just drew and we use that to condition the function for generate x2. Okay, and then we do that, and then, all right, so let's just try this, okay, and we'll see if this works. I just coded this right now, so, oh geez, okay. Error in xi, see, number of items to replace is not a multiple.
Maybe.
Oh, in our norm, I have to say I only want one value. Okay, yes, that makes sense. All right, I specified my functions wrong. Okay, there we go. Now we're working. All right, so let's just kind of take a look at this. Plot x. Oh, that looks pretty good. That looks like, so we started off kind of at this bad location, right? We started off at, where did we start off? 3, 5 or something? 3, 5, and so, you know, it kind of generated some wild values in the beginning, but then, you know, towards the end, we got quite a bit. Let's just try 10,000 of these things. All right, and then let's just plot this. Plot x, let's do PCH equals 19. Oh, too many, okay. CEX equals 0.1. Let's do that. Okay, I mean, that looks pretty good, right? I think so. And then let's just try like a different row, okay? I'm gonna do like negative 0.9. Let's see what this looks like. I don't know, it runs quick, so. Yeah, I'd say that looks pretty good to me as far as bivariate normal generation of stuff goes. So, okay, anyway, that's the Gibbs sampler. We'll talk more about this, and we'll look at some applications of this, okay? I know all of our things have just been bivariate normal things because that's like a simple thing that maybe we can grasp easily, but it can definitely be expanded to other things. Have a happy Thanksgiving. I hope all your travels are good, and we'll see you guys on Monday. Oh, I've also extended the homework deadline, so it's not due the Monday that you get back, but like a week from today, okay? Or no, a week from Friday. Okay. All right, we'll see you guys.